Hi, everyone. So this morning, what I want to do is try and convince people basically of two things. The first one is that Python is a great tool for bioinformatics, and I probably, given this audience, I shouldn't have to convince you. And the second one is that learning about bioinformatics is a great way to learn Python, and maybe, hopefully, by the end of the talk, you'll be convinced of that. So first, a quick disclaimer. I'm not a bioinformatician. I've got a computer science background. I do bioinformatics as a hobby. But if there are any real bioinformaticians in here, you'll probably want to say, hey, that's wrong, or that's an oversimplification. So a little bit about me. I lectured for about 7 years, but I've also run a lot of training courses. I've run training courses where I work at Bureau of Meteorology in Python. So I've got some experience about teaching Python. I love doing it. And I've also run training courses, as I say in the next point, for a group of bioinformaticians. But these were C++ courses. So I taught people doing bioinformatics C++. And when doing this course, I was looking for problems that were in their domain so that I could teach C++ concepts. And when doing that, I came across this site on the internet called Rosalind. And what Rosalind is a site with about 300 bioinformatics problems. You can solve them, you submit your answer online, it checks your answer, and if you get it correct, you get 1 point, basically. And as you solve more and more problems, you move up the scale, and you can rank yourself against other people doing it. So if anybody's familiar with Project Euler, very similar concept, but these are bioinformatics problems. So the problems we're going to see today are all based on problems that came off Rosalind, but I've tried to keep it close, but not too close. So just a quick introduction in case you've never heard of bioinformatics. What is it? Bioinformatics is this multidisciplinary field covering computer science, biology, mathematics, and statistics. So what it comes down to is during the 60s, 70s, 80s, people started sequencing DNA. From a computer science perspective, DNA is just this long string of A, C's, G's, and T's. It's a lot more subtle. If anybody went to Darius' talk yesterday about bioinformatics, often you'll have missing things, you'll have gaps, you'll have transcription errors. But if you're a programmer looking at DNA, basically you say, this is a string. Fantastic. So I started typing in some random stuff there, and I don't know if you've ever tried typing in 4 random characters. It's actually quite hard. So I got to the end of the first line, and I thought it would be much easier to write a quick Python program. So I wrote 2 lines of Python, and it was a lot quicker, and that generated that previous slide. So, that's not a real bioinformatics problem, but it's good for generating test data, and I have used it for generating test data. So. Okay, the first problem we're going to look at is to determine what we call the GC content of DNA. And so we've got this string, it's got A, C, G, and T, adenine, guanine, cytosine, and thymine. And we want to find what percentage of a particular strand of DNA or sequence of DNA is C's and G's, because for some reason, bioinformaticians find that those areas that are rich in what they call the nitrogenous bases are actually far more interesting than the areas that aren't. So when I run a Python course, after the first morning, most people would be able to write this program, and I think everybody here should be able to follow it. Basically, we go through the string character by character, and if it's a C or G, we add 1 to a counter. So it works, but it's not particularly Pythonic. So the next thing we do is we say, well, let's look at using a list comprehension. So basically we say, okay, let's take each base in the string, and if it's a C or G, we'll count it, we'll add it to this list, and at the end we return the percentage of C's and G's divided by the percentage or the length of the whole string. So to me, that's a little bit more elegant. However, we can go one step further. And we use the count method of the string. And we say, count the G's, count the C's, and divide it by the length of the string. And to me, this is what's great about using Python for bioinformatics, that it just seems that Python was designed to solve exactly this kind of problem. It's clear, it's simple, somebody looking at that program should be able to know exactly what it does, assuming you know can't. But the other side of the equation is that this is actually a real-world problem. A lot of time when teaching programming, we make up all sorts of problems like calculate how much paint you need to paint a room 4 meters by 5 meters, whatever. Nobody ever needs to do that. But this is something people actually use. So the next one we'll look at is what's called reverse complement. So I think everybody's aware that DNA is a double helix. Somebody got a Nobel Prize for discovering that. And G's always bind with C's, and T's always bind with A's. So if we have a strand of DNA, we can either look at it in one direction, going GT, CC, G, etc., or we can look at it in the other direction, going CC, AG, etc. So for example, if we're looking for the sequence GAC, we may not see it in the top row, but when we're looking at the bottom row from right to left, we do see it, and that's called the reverse complement. So the second problem is, given a sequence of DNA, such as the top row, find out what the bottom row is. It's not particularly hard, but once again, in doing this, we find it's a very natural mapping for a dictionary. A dictionary works perfect for this sort of problem. And once again, a very simple solution where we go through each base and we create a list, and then at the end we return the reverse of the list after having mapped the A's to the T's and the G's to the C's. So once again, somebody after half a day of learning Python in these courses should be able to do that. However, we can do better. And so in this one, we once again have our dictionary, but in this time we use a list comprehension. And I've used the array slice notation to reverse the list. And I think a more elegant, slightly more robust solution. I've also used the join operator. So hopefully people are starting to get convinced now. The next problem we'll look at is one that actually we learned about in computer science long before I started looking at bioinformatics, called Hamming distance. So if anyone was at Daria's talk yesterday, she spoke about single nucleotide polymorphisms, or SNPs, where you've got two sequences of DNA and they've got one difference between the two. One of the bases is different. Other reasons is when we sequencing DNA, often there are errors in the sequencing. So instead of recording a C, it may record a G. So we may say, okay, we'll consider two pieces of DNA to be the same if they differ by less than three positions. And so that 3 positions where these two things differ is called the Hamming distance. In other words, in that example, we have a Hamming distance of 3. So once again, somebody's learned a bit. Usually the courses I teach at the Bureau, the people come from C or C++ or Java background. So they're used to this procedural way of looking at things. And because we've got 2 sequences, it's a little bit more tempting to say for iron range length of left-hand side. As Raymond Hettinger said, if you need to say iron range len something, there's probably a better way. So I thought, okay, well, can I come up with a better way? So I thought about it a bit and I came up with this idea, create 2 sets. The first set is the position and the base of the left-hand string. The second set is the set and, position and base of the right-hand string. And using set difference, it will tell us how many difference. But I didn't really like that because it's not really telling us what we're doing. So I came up with what I think is a slightly better solution. What I've done now is I've zipped the 2 left-hand side and right-hand side together. I've said, pick out all the tuples where they're different and count how many you've got. So once again, it's down to 1 return statement. But what I like about this, and where we come back to learning Python, is I think it's a really nice motivating example for the zip operation. Some people have difficulty getting their head around zip, but if you look at those 2 rows, and you think, okay, what I'm doing is I'm zipping them together like a zip, and I'm counting wherever the 2 bits don't match. So to me, that's very clean, very concise, and when I look at that, I think, yeah, I'm pretty sure that that's doing exactly what I want. Okay, get to slightly more interesting problems now. Finding motifs. So the first thing I'll explain what a k-mer is, and then we'll get onto motifs. So motifs are short recurring sequences or patterns in a DNA that are presumed to have a biological function. So if we see the same pattern repeating in DNA, we say, well, maybe there's some reason why this pattern is repeating, because nature generally is fairly parsimonious. It doesn't like to waste. So when there are repeats, there's often a reason. And so we look at some DNA, we say we want to find out, given this string of maybe 1 million bases, look for the things that are the most commonly repeating. And we may say, I'm interested in sort of sequences of 10, and this is where this idea of a k-mer comes in. So if we're looking for 7 long, it's called a 7-mer, 7-MER, I guess mer from polymer. And if we're looking for 12, it's a 12-mer, etc. So the first program is just, given some DNA, print out all the, in this case, 5 mers, k is equal to 5. We usually use k for k-mer. And so that's pretty straightforward. We've introduced the slice operator. Once again, nice motivating example. But we're not interested in listing them. We're interested in counting the most common ones. So we'll just go to our next program, and this is where we do count the most common ones. And once again, it's a very procedural program. We start with an empty dictionary, which is a common way of counting things. We go through all the k-mers, and if they're not in the dictionary, we add them. You'll notice I've got an if statement in that program. Generally, if you can get rid of an if statement, your program gets simpler. So what I've done in the next slide is I've used the default dict from the collections module, and that just gets rid of the thing. And then the last 2 lines, all equals sorted. So what that line is doing is we're sorting by the value, not by the key, because we want the most common, so the ones that appear most frequently, that will put the most common ones at the end. And we're printing the last 5 items in that dictionary. So, but it's not a very elegant, as far as I'm concerned, program. So let's see if we can do better. I use the counter from collections. I use a list comprehension to find all the k-mers, very straightforward. And I just say print the most common 5. To me, that's just great. It's like Python was written for bioinformatics when you do stuff like this. And it's so expressive. Nobody can read that and not knowing you're looking for the most 5 common k-mers. Okay, we'll have if people's brains are hurting a bit. Oh, I should have mentioned at the beginning, all these slides will be available, so don't worry too much. So we're going to look at rabbits for a second. Fibonacci numbers. I think everybody's written a Fibonacci routine if you've ever written a computer program. It's at this stage nothing special about it. One thing we do have is I've used that tuple unpacking in that line for iron range n, child comma parent equals parent comma parent plus child. In other words, for each generation, each parent has 1 child, and the number of parents is equal to the number of parents plus the number of children, because the children grow up and become parents. If you've ever written a Fibonacci function, there was always that thing, do I add the parents to the children first, or do I first print the result, etc. Using a tuple, you don't have to think about it, really. It just works itself out. And if we run this program, it prints the first 10 Fibonacci numbers, 1, 1, 2, 3, 5, 8, etc. Okay, so this would be very similar in any language. Why do I pick this example as a good motivating thing for Python? Because in Rosalind, they ask for something like their 150th Fibonacci number, which in fact turns out to be that number. So that's not a series, that's just one number, 161305. It's a really big number. If you had used C or Java, they would have overflown and you would have got either 67 or minus 2315. Or you could have imported libraries, installed those libraries, worked out how to use them, etc. Python, it just works. Probably tired of me hearing, but fantastic. Okay. We've got 2 more examples. This one is calculating what they call minimum skew. So earlier we said areas rich in CG are interesting. it turns out that if the ratio of C's to G's is high, so we've got a lot of C's close together, it's even more interesting. So what the skew is defined as is we start off with 0. Every time we see a C, we subtract 1. So the first two characters are CC, so we go from 0, -1, -2. If we see an A or a T, we just keep going. A G, we add 1. And what we're interested in the end is the index of all those positions where that running list was at its lowest. So in this example, we see we've got a -3 in the 1, 2, 3, 4, 6th position. So we assuming that we don't go below -3, we would print out 6. If there were two -3s, we would print out 6 and 12 and wherever else at -3 occurred. And so it started off with this program. It's just, simple. Once again, you just quickly attack it. And we say that we'll just keep running along that string, and each time we'll keep a list, which is the running total. And as you can guess, we can probably find a better way of doing it. So the first thing I did was I got rid of the, I've gone back a slide. So we had that if CH in CG. Well, we don't have to check because our dictionary only has a C and G we're checking. So in this example, I just put all 4 characters into the dictionary. And that means, so A and T are both 0, so I can just keep adding. It makes it a little bit simpler. So let's make it even simpler. So in the next thing, I wanted to use a list comprehension, but that meant I had to write a function to do that. And when I wrote this function, because with a list comprehension, it's really hard to get memory. In other words, this accumulation of what went before. So I wrote this function, and I needed a global variable, which I didn't really like. I don't like using globals. So in the next iteration, I used that same function, but in this one I used, it's really a hack where you have an array which is a default parameter. So it gets initialized the first time, but then remembers its values. So that was just as ugly as using a global variable from my perspective. So the next thing I decided, okay, I'll use a generator. And that way I got rid of the global variables. I got rid of the ugly hack. Fantastic. And it works, but the generator actually knows about this dictionary. And really all the generator is doing is accumulating. So it shouldn't have to. So basically what I did is I renamed it accumulate because that's what it's doing. I moved the mapping of the characters onto the dictionary into the main part of the code, which is where it belongs. And so my dictionary really just accumulated any list of numbers, and each time it was called, it would return that value. So this worked, but I looked at it and I thought, well, in a way, it's just as complex as the original code. I've still got a for, I'm now using a generator, I'm using function calls, etc. So I thought, okay, this is where I pull out the big guns. So I used NumPy, import NumPy. A is equal to np.cumulative sum of that list, list comprehension. Print np where a equals min of a. And once again, also this other part, the last 3 lines where I calculated what the minimum was, then ran through, and then was also pretty ugly. So I got rid of that in one line with the np where. I was showing these slides to somebody and they laughed, and I said, what's wrong with them? And they said, like, are all problems in Python reducible to one line? And I had to say, well, actually, these are pretty simple problems and things. So the next one, I'll just quickly show you a description of a problem. It's called hidden Markov models. I'll try and explain it quickly. And so hidden Markov model, assume we've got a machine, and this machine is either in state A or B. If it's in state A, it emits an A. If it's in state B, it emits a B. When it's in state A, it will emit an A, and then it will change state, and it will go back to state A with a probability of 0.2, or it will go into state B with a probability of 0.8. If it's in state B, it will emit a B. It will go back to state B with a probability of 0.37 or back into state A with a probability of 0.63, roughly. Okay, so the problem is, if we've got a string, B, A, B, B, how likely is it, what's the probability that it came out of a machine with those probabilities? And that's hidden Markov models. You can spend a semester at uni studying that, or you've just learned it in 1 minute. Okay, so when we look at this problem, or when I looked at this problem, I thought, okay, this to me looks very much like a graph. Okay, we've got 2 vertices, 4 edges, and so we could model it as a graph. Using Python, to me it seemed natural. If we're modeling a graph, we have a dictionary. So I created a dictionary called transitions. And the transition, because in Python a dictionary can be a tuple, we can say A to A is 0.193, A to B is 0.087. So we've modeled that finite state machine, that Markov model. There's our DNA. It's not really DNA because it's B's and A's, so, but all the other things were DNA, so I've called it DNA. According to the problem, we could start with equal probability in either state, so we set our result to 0.5 for the start condition. And then what I did is zipped the string to itself, but shifted by 1. And that's the zip DNA, comma DNA of 1 colon. So that gave us BA, AA, AB, etc., as a list of tuples. And so all that was left was to say, for CH in that zip, result times equals transitions. We run it, and so basically what happens with Rosalind is you run these programs, it comes back to you and says, like you'll give it a number, I forget what the result was then, it's a really small number, and either you correct or incorrect. If you correct, you get your mark. And I left this comment in my code after I'd written it. So it actually worked the first try, which I was quite surprised by because I didn't really understand hidden Markov models. So what can we conclude from this? Well, Python is a great language. So I've solved almost 200 of these problems, and I gave you a sample of really short, quick, easy ones. These mostly took less than an hour to solve. There's some that have taken half a day. There's some that I'm still working on after having worked on one problem for over a day. But each step of the way, Python seems to have been guiding me, helping me. It's like, it really feels like you've got a partner there. Whereas often with some programming language, you think, oh, this language is really getting in the way. It's, I wish I had something better. So that's my first thing. The second result is that I found Rosalind, this rosalind.info site, a great source of small problems to solve. So often on Reddit or whatever, you'll read somebody saying, look, I want to learn Python. What's the best way to go about it? If you want to learn Python, and you don't really have, something applied, fantastic way to learn Python, and at the same time you'll be learning a lot about bioinformatics, because for each problem they explain some of the bioinformatics principles behind that problem. Finally, I just sort of added this. To learn, we need to solve problems and relentlessly improve our solutions. So, the first solution looks okay, but you can always improve it. And this morning at, I think, one of the keynotes, Damien was saying that how with Python you just always continually learning, there's new stuff to learn. So I think that's great. And thanks very much. So if you're interested, the slides are there. And yeah, you can use your mobile phone maybe.
Thank you, Martin. We have 5 minutes for questions. I want to see hands up in the air. Okay, I have one question.
Yes.
For you. You mentioned that bioinformatics is, or these problems in bioinformatics are a good way to learn Python. So you learn more about Python, how to solve problems. Have you applied any of these methods that you learned through bioinformatics to solve other problems?
I've applied the things I've learned through learning this to solving other problems. So sort of, as I do this, I pick up little bits of Python, and particularly things like the Hamming distance. I find, there's a lot of stuff where you think, okay, I've got this problem. I did this for a Hamming distance. I'll do it for something else.
Yeah. Okay. Yep. First,
Hi. So you said that you'd been teaching Python at the Bureau of Meteorology. Have you ever introduced the Rosalind problems to those people, and how did they handle the context switch, if you did?
Right. So I guess one of the things and why I used Rosalind when I was teaching it to bioinformaticians is I always try to look for domain problems. So when I'm teaching at the Bureau of Meteorology, I look for problems to do with weather, with climate, with water, etc. So I guess the simple answer is no, I haven't.
Hi, that was a great talk. When I was at uni and when I was doing my PhD, we were really encouraged to use R. Do you find that the culture push in using Python is quite difficult to get across for long-term R users?
I've met R users that have moved to Python. I've met R users who say I'm perfectly happy with R. My feeling is that as a lot of people, when they move from simply solving, let's say, a problem like that, to having to pull information down off the internet, having to deal with files maybe on a network. Where we work, we deal a lot with NetCDF files and that. Start seeing some advantages to Python. So I'm not, even though I want to evangelize Python and think everybody should be using it, I'm not out there to convert our users. So.
Thanks. Hi, Martin. I teach 15, 16, 17 and 18-year-olds who have never coded before. And some of those problems are the kinds of things that we use, and we find that that's fantastic. But how do we direct them to resources that will help them identify the second and third and fourth and fifth iterations of your problems? Because when we're sort of teaching them the basics of loops and things early on, the idea of using something like zip is not going to occur to them. So I guess I'm really curious to find out how we would guide them to those kinds of things, because the documentation is very, very daunting for a student who is struggling with these things for the first time.
I don't really have an answer for that. I'd love there to be an answer. I think part of it comes from people's motivation, that when people are motivated to learn, they pick up the resources. It actually just so happened that I got home last night and my daughter, who's 13, had been given a problem at school, which was to calculate pi using random numbers. And I sort of showed her a quick solution in Python, and then she said, oh, we have to use Scratch, and there was a lot of pain there. Having said that, I think part of it has to be self-directed. People basically have to want to learn, and I don't know how to do it, I guess is the simple answer. So.
Okay, before I forget, we have a gift for you, Martin.
Thanks very much.
It's the mug with the flying tramp, I think. I'm not from Melbourne, so I don't know. We thanks Marty one more time.